this presentation is about Key Management Service protocol, and that's not a new protocol. Actually, it was introduced back in 2010 in UEFI 231. So, touching such a dusted subject, I feel like some explanation is due. Why we even bothering to talk about that? So, even though the protocol is old, we believe it's kind of underappreciated. It's one of those less known protocols. So, on one hand, we believe it has some practical value. It can help solve some real-life issues, like if you will be covering some use cases, you'll see those are not, by no means, some exotic use cases, probably. A typical firmware does, at least one of those. Yet people are not using the protocol, which means typically there are some closed source solution, which is fine, which works, but then doesn't necessarily scale well, especially when the ecosystem grows beyond the boundaries of one particular company. So we tried to structure the presentation in a way to we try to answer the questions why people are not using the protocol. So first reason, rather simple, maybe people don't even know it exists. So we kind of presented the protocol, we are showing what it can do, how it can be used, what are the use cases, what are the implementation options, and then we are going a bit in depth with a specific implementation with the KMS service based on TPM device, because after all, that's maybe the most widely available security device. So let's start. So yeah, the protocol is defined in the UEFI spec. This is the interface structure. Looks a bit intimidating, but actually almost half of it is the data members that just convey some information about supported capabilities. So as far as the API, the functions, the protocol has the kind of standard functions that you expect to see there, the key generation, create key, get key, delete key. Add key is an interesting function. Essentially, add key allows you to enroll external keys that you received from somewhere else into the key management service protocol's infrastructure. And what's the value of it? One, it provides you a secure persistent storage for your keys. That's a typical problem, especially when we discuss internally some improvements. How can we make things more secure? Maybe we'll encrypt something, protect something. Always these questions comes out. Okay, how do we manage the key? So essentially, that's one way. If you have a trusted KMS implementation, you don't have to worry about that. You just use the function. So that's one capability. Also, another reason you may want to use add key, you can standardize management of all your keys. You may have different key providers, each one with each policy, with different auditing infrastructure. So you can kind of have your central implementation, and then you can enroll all the keys into that central implementation, so that you have a standardized, as I said, maybe validation infrastructure, auditing, login infrastructure. So potentially with the KMS, essentially you can build a cascading set of those key services. There can be multiple instances which kind of play together. The protocol supports multiple key types, meaning key types suitable for different encryption algorithms, different formats. It also supports client-based key handling. It means it has this function, register client, which essentially provides the ability to separate keys owned by different consumers. So you first register your you provide the client information to the server, and then you have to pass that client identifier pretty much into every API. So At minimum, it's a convenience interface that just allows you to separate your keys from somebody else's keys, and at maximum, it can be a security mechanism because the KMS can actually validate who's trying to retrieve the key. So the protocol also supports association of some custom data with the keys. You can associate some attributes with the key or a client data. And that's also an interesting capability. It's actually like a dual-edged sword. On one hand, that's a way to implement a lot of improvements potentially. Like pretty much, if you look at every API, get key, create key, you're passing some blob. You have the ability to pass a blob of client data. So you can. It's almost like a parallel exchange stream between KMS service and the caller. So it can be again as simple as maybe, okay, let me store my custom token along with the key, or it can be as sophisticated as some maybe security validation state machine, whereas for every call you have to prove, okay, I am who I am. That's one side of it. Another side, of course, the spec just says, okay, you can pass custom data, end of story. So whatever you do becomes a proprietary solution, which kind of to a certain degree diminishes the value of a standard API. And finally, it provides some ability to do on-demand service startup. So what we are talking about here, of course, the default method of doing on-demand startup in UEFI is the UEFI driver model. And that's still there, that still can be used. But in some cases, it's not very convenient to see. The decision what to connect and what not to connect is typically made by the platform, like PDS. And in some cases, platform may not be aware, for example, if key management service is needed or not. Maybe you have some secure storage which with its own policies, maybe it needs that key every 10th boot or something like that. So, of course, the driver itself can call connect controller on demand and just initialize whatever it needs. But it needs to know the device path, which we'll see there could be a wide range of underlying KMS implementations. You don't necessarily know that device path. It can be built on top of the network, or it can be built on top of TPM. As we just heard, TPM is often onboard device. You don't even have standard device path for it. It will most likely be some vendor device path or something like that. Maybe once we embrace the device 3 thing, it should be standard. So essentially, so the driver that needs KMS would have the only option is, okay, let me connect everything, which is not a good thing. So instead, the KMS protocol provider can publish a protocol without fully initializing it. And then there is a get service status function, which is essentially init on demand function. The consumer, before using the services, can check if the service is not started. The caller can start it on demand. So it's like a second level of flexibility to say the good time. So the use cases. Most typical one, I said it's rarely used, but it is used. So typically when we see that it is used to manage secure storage, to unlock or decrypt. And that's a good example in the sense that it shows the interoperability between different, for example, we have a RAID controller with the notion ROM that comes from company A, and then of course it's plugged into the system board with a firmware implementation from vendor B. So that's where it's kind of useful to have a standard interface that both sides can use. Then the KMS service can be really instrumental in managing passwords. It can range from machine maintained passwords when user may not even be aware that there is something going on, or it can be machine managed passwords that are like that are derivative of some user action. Maybe user enters the main password and then we generate some specific, retrieve password for a specific device. And then of course we can directly manage the user password. So there are two main ways to use KMS to manage passwords. As I said, it provides a secure storage capability, so we can simply, just trust KMS and then, get those passwords. Or it can be used to facilitate encryption. And then after that we can store passwords in a non-secure storage such as in the RAM, for example. Another potential use case is device coupling. For example, you want to make sure your blade solver only works with the specific server rack. So then you can have in the rack infrastructure you can have that KMS service provider, and then in your server you can have a driver that talks to that provider and then like unlocks system only if you are connected to where you should be connected. Device attestation. So we also had presentation about that yesterday. So UEFI 2.10 adds some infrastructure for device attestation. So before that, maybe KMS would have been of more help. Now with this new infrastructure, it is still useful, but it becomes more of a facilitator, maybe a mechanism behind the implementation. And then encryption of some critical pieces of the firmware. For example, if you remember HSTI, initially when the spec was released, it was some hope that maybe this code will somehow be protected, so that because it's a critical piece of code, and never happened. Maybe absence of reliable key service may be one of the reasons. And like last example, replay protected count-based storage. This is also, I think that requirement is in the Windows logger requirement, but it was also, implementation was problematic, but essentially you need a key and you need some counters to implement it. That potentially can come from the KMS. Now, key management service. So it's good to have a nice API to get the key, but of course it's as good as the protection it provides. It has to be trusted. So it has to be secure and reliable. Of course, when I write my code, I just want to call a function, but then at the same time, it should be protected from the attacks. So that's one of the areas that maybe more effort is required, but there are some mechanisms to make the service pretty secure. So obviously, some capabilities can be disabled at certain stage during the boot, like the most obvious being like SMM ready to log, something like that. As I said, the service manages keys based on clients, so it's also possible to, for example, disable certain capabilities for certain clients. The register client interface can be used to kind of, you can deny service to certain clients or deny service at certain point to certain clients. And then of course there are always those corner cases, like okay, you have your KMS, it works perfect, but what happens if you can't get the key? Like on one hand you need a recovery mechanism because, for example, if you're getting your keys over the network and network is not available, still should be able to log in. At the same time, maybe that's a bad guy trying to break your system, so he should not be able to log in. So that's whole another kind of area, but it's important at least to keep those in mind, to think about those so that, again, that's secure by design, so that you cover those scenarios at the, before the deployment, as a part of the design stage. And final implementation options. Essentially, it can be built on top of any, device that is capable of producing those keys. It can be local devices, TPM, BMC, DSSCM, some PCI, USB card, whatever. And it can be remote. Like for example, I think a few years ago we did presentation on key management service built on top of key management exchange protocol, which is a network kind of standard for key exchange. Now, today we'll talk about the building KMS on top of TPM. As I said, that's the most readily available device, and also that's device that's kind of always there. It's of course it can get broken, but availability is pretty high, especially compared to remote devices. So Fred will cover that.
All right. So Felix, I hope Felix got you guys sold on KMS. I'm going to talk about a KMS implementation based on TPM, and I'm just going to ride through this slide because Felix already talked about it, right? TPM is just everywhere right now, right? Just about every platform shipping has a TPM, right? So it's available. Well, I guess another thing though is the TPM can also be used as a backup to a KMS over IP, right? Depending on how you set up your policies and infrastructure, right? And I'm going to go a little bit into that on the next slide, but I think that's the main touch on this slide. Now, UEFI defines KMS protocol interface, right? But doesn't provide any information about specifics about implementing KMS, right? So then we have to look at other industry standards that can kind of direct an implementation, right? So one area we are going to look at, we have to look at will be the TCG forum, right? And what kind of specifications are coming out of there, right? And here I have a list of some of the specifications that are relevant, right? Because there's the PFP specifications that's relevant to the firmware. There's the DICE specifications, right? That's kind of helping with device identity, but more so, you can get information about how to create your keys and what are the key properties that you should use, right? There's also the SP 800-133, right? That has information about what key properties, right? What key properties are good for this KMS implementation, right? When you're creating your keys. So now, yeah, we have a KMS implementation, but the implementation, it will be defined by your needs. It will be defined by your platform needs, right? And it will also be defined by how you set up your platform policies, right? TPMs are very flexible in terms of how you can set up TPM policies, but you have to know what you're doing and you have to kind of think ahead, right? So if I'm going to use a certificate infrastructure, right, where I'm using this TPM as a backup to a KMS server, it means you have to be able to, it means you're thinking about recovery, which means you have to have some form of way to load certificates into the keys, into the public keys, into the TPM, and be able to use them, right? But it has to tie into your whole policy infrastructure, right? It has to tie into whatever solution that you're trying to present, right? And also, obviously, the keys that you create in the TPMs are good for creating keys, for sure. But the keys that you create have to have certain properties if you're going to be secure, right? In terms of hierarchy consideration, I'm sure most of you guys are familiar with TPMs, and I'm sure a lot of you guys are also aware of the TPM hierarchies, right? There's the storage hierarchy, endorsement hierarchy, and platform hierarchy, right? And for this implementation, I think most likely the best place to do an implementation would be under platform hierarchy, right? Because you're not exposed in storage hierarchy with like TPM clear, right? Those kind of information and thinking ahead are important to a wholesome implementation, right? So this is just basically a simple implementation, right? Where you have your TPM device over there, and obviously you might have some TPM objects that you're going to create, TPM NVRAM objects. or you're going to create TPM key objects, right? And they're going to have some properties, right? And you have to protect these objects because in the grand scheme of things, you don't want these objects to always be available to just everybody, right? You want to be able to control when these objects are available and when they are not available, right? And you just have a KMS interface layer that's just going to respond to KMS requests like get key, create key, get ID or the create ID, right? So this is just a sample implementation, but it has its flaws, right? This implementation has its flaws, right? Because we're talking about using a TPM on a platform, and the flaw is basically you have an advanced attacker that could actually be able to either inject cycles on whether you're on the ITC or SPI bars, right? You can have an advanced attacker, right? Or you can have also an advanced attacker looking at what you're pushing in and out of whether key ID or keys that you're pushing in and out, right? So a good implementation has to put these into consideration, right? And one way you can kind of fix that is, well, the next versions of TPMs coming up have the SPDM interface, so that will help you to close that flaw over there, right, with the TPM and the HSM layer over there, right? But then you still have the issue of if an attacker can actually read your keys or actually get your key ID and say, hey, I want to get this key ID. We don't know what the person can use with this key ID, right? But we still want to have we still want to provide some form of protection to this access to this key ID, right? Because who knows, maybe he found a vulnerability and all he needs is just to get a key ID and just inject it somewhere else, right? So one way you can work around that would be to have the KMS interface has a client registration interface, right? So you can have a client registration negotiation with the client where you can either set up some form of session or some PKI session with the client. And on the SPI and on the TPM with the SPDM responder over there too, you can set an SPDM session over there as well. Now, if you don't have TPMs with SPDMs, right, you have, I think the TCG group has a paper out for attacks that are based on advanced attackers that are able to inject cycles, right? So you can try to use that implementation to show up your implementation over there, right? And that gives you a wholesome, well, not fully wholesome, but it gives you a better implementation for a solution where you're providing KSM based on TPM. Now, of course, there's some challenges, right? The devil is always in the details, right? And it's always going to be affected based on your platform needs, whatever design solution you're providing. And well, if you're going to create policies based on PCRs, you could, but you have to expect that if you flash your BIOS or you do firmware updates, you have to have some form of recovery, right? You can create policies based on TPM env-realm or TPM authorize or TPM sign, and policy sign. And those are all good, but they all have their drawbacks, right? Because if you're going to use TPM authorized or TPM policy sign, it means you have to look at your certificate infrastructure, your certificate hierarchy, so that you can provide a wholesome solution, right? I would like to say I have a magic bullet that, hey, this is what you do, and you can use this everywhere, but it has to be something that you think through in terms of how you implement it and how you're going to use it, right? Yeah, so this will.
So we wanted to make sure I'm not relaxed until the spec is done. That's why the last slide is also mine. So we described kind of nice features of the KMS, but of course, it can be improved, and so that's kind of another hope that maybe by raising the interest we can start the discussion, and that's the first step towards improving the interface. So there are a few things. Like first, the protocol needs to be, let's say, proofread, because since it's not actively used, there are some language that is not precise, that sometimes it's not clear who's allocated memory, who's free memory, what is persistent, what is just maintained for the duration of a single boot. Sometimes you have to imply that. Then, thread model would have been nice, because of course that's the key property of this protocol. It has to be secure. Of course, its thread model does not belong to a spec, but maybe some white paper or something would be nice. And then some protocol improvements is also due. Like as I said, the protocol is 10 years old, so now it's time to maybe add support for longer keys, maybe new algorithm like I believe elliptic curve is not currently supported. The protocol, as I said, certain services can be locked at certain stage of the boot, but currently it has to be implemented by the KMS driver, whereas it's often governed by the platform policy. So having an explicit service to lock would have been nice. Then we can separate platform policy from the KMS implementation. Also, as I mentioned, the implementations can be widely different, providing different capabilities. Like, for example, TPM-based KMS would be much more limited compared to network-based KMS. So it would be nice to have some way to get this information. It's partially possible by analyzing the device path, but that's not always precise. So maybe another way to do it, so the protocol already has a service GUID data field, which currently the spec just says that's maybe a GUID that identified the service. So maybe one approach is to come up with some profiles for service types. That way, kind of the consumer can get an idea what kind of service is dealing with. That's especially useful because, as I said, the protocol allows to potentially chain multiple levels of key management. For example, you can have a remote-based or network-based KMS to enforce like whatever corporate policy, and then local KMS based on TPM, for example, that is used for recovery or for caching purposes too, so that you don't have to send a network request on every boot. And of course, if you're trying to make it more secure, sooner or later you start thinking about moving it to SMM. So that's maybe we should think if it makes sense to have a PI version of that protocol that can be published in the MM environment. So this is it. Yeah. Any questions?
In terms of improving the capabilities of PMS, is there a immediate implementation of reference one?
Yeah, no, I believe the header is there, but that's about it. There is no.
Yeah, it is going to improve availability of having this you mentioned as an opinion, based on something that would be interesting to have. Especially if you could bring that as an experimentation sandbox to some of the
Yeah.
Hey, there's a Raspberry Pi in Housekeepers.
Yeah.
You have a sentence there about IAG currently not being able to rely on this being implemented in a third-party platform. Do you expect that IAGs will ever come to a point where they'll be able to trust the security implementation of the platform and use that to authenticate, for example, updates or device and that kind of stuff? Because from past life, I've never seen a situation where, as an IHV, when you need to ensure that the device works on a broad range of platforms, whenever we're talking about securing, for example, firmware updates or any other kind of critical piece of the code, it always has to have been done on the device. There's no question about trusting the platform to authenticate, for example, with firmware updates.
Yeah. It's a question, essentially a question of reaching critical mass, because we are, like, we have, as I mentioned at the time, we have two implementations over the network and over the TPM, and actually it started as like a three-way conversation between IHV, like us, and some like OEM that wanted to ship a device on their platform. So, but now I imagine that IHV, they have this device, so they will probably want to broaden their scope. So they will start telling to people, okay, we are compatible with this protocol, go add it to your implementation. Then maybe more OEMs will start asking for that protocol. So as you know, once a critical number of large players requires that support, you know, it will become widely available. But of course, I cannot guarantee. So it's a process. So may or may not. But all we can say from our side, we see a value, so we are kind of trying to popularize, but one step at a time.
Can you touch a bit more upon the requester authentication? How would you go about verifying that the requester really is who they say they are? And how do you do that in a way that allows this protocol to still make sense in that the overhead of supporting that doesn't exceed the value provided by the protocol?
Yeah, so there are multiple layers. So first, as I said, in each API you pass your client ID. So it can be as primitive as you know, like you have fixed list. Okay, 1, 2, 3, 4, 5. If it's 6, go away. Or it actually potentially could be some kind of a security token. For example, if there is some, you know, other source of some security tokens is available on the device, then you can potentially pass that to a KMS. For example, that's especially useful if you have the network KMS and then the local client have some like TPM, some local device that you can use as a source of those tokens. You can pass them to be validated on the other side. So that's one level. But then, of course, UEFI is not an operating system. You don't have inter-process protections. So how do you even know that you are being called by? So to that, unfortunately, we have to trust to existing infrastructures. Like number one, we have that end of Dixie event, that's our platform trust boundary. So if you have a secure update, if you have like measured boot, then you can reasonably be sure that whoever is calling you is part of your platform firmware, part of your trusted boundary. Then if you want to go beyond that, we have secure boot. So those we all know what are the limitations, but that provides some level of protections. So there are like narrow things that can be done within TPM in KMS implementation, and there are wider things that is like UEFI wide like challenges. That's why I'm saying maybe kind of having some kind of threat model, white paper related threat model would have been useful. Yeah.
So on your, I have 3 questions, but I'll start with the last one and maybe work back, or Dick will throw out the big cane and pull me up my mouth. So the MM version, were you thinking using SMM or Trust Zone just to protect the KMS implementation during the pre-OS? Or were you thinking of having the KMS TPM style capability through the life of the platform even at runtime? What did you mean by that?
Yeah, I meant pre-OS because that's kind of one way to make it more secure. Like that's what I mentioned. Because for example, if your consumers are also within SMM, then that's kind of an extra boundary.
It's our typical model of process isolation
Yes.
using SMM, but you weren't trying to say have this through the life of the platform. Because we tried that before, and the challenge we had was since TPMs are dual ported, even though the platform auth gives sort of ownership of the platform code, if you're trying to do it at runtime from management mode, and Windows is trying to hit the TPM, it's not a dual port source. Okay.
Yeah, that managing device from firmware and OS is not.
Okay.
And I think even if you did that, the PC client people would be mad at you.
Yeah, I think Amy Adele would probably send some nuclear missiles.
Exactly.
Yeah. And then I guess the only other challenge you have with doing the platform auth is you have to have a secret to assert the platform auth, right? Because today, since we don't use it, we just generate a non-SIP boot and cap it. So you have a management challenge of platform auth still, so outside of KMS, right?
Yeah.
So you have to devise something. Is that what you guys were talking about with DICE? Do you derive it through a CDI or something, or what was your DICE thing?
So currently the implementation actually uses, the current implementation actually uses platform auth to a certain point, and for most platforms, platform auth is locked at the end of this. Like for most platforms, platform auth. Yeah. So we create a TPM-MV policy, right, that we'll use after the platform is locked, right, and that gives us some time range where we can say, okay, between these range, you can come in and say, hey, I want to create a key, give me a key ID, right? And I think the locking, we do a lock on this on the MV policy, I want to say before the end of BDS.
Okay.
Right? So yeah, that's one of the, like I said, the devil is in the details, right? Because you can't depend on platform auth to be available all the way through.
Right,
So
that's a high value asset
Yeah.
that everyone's going to go after. So.
Yeah.
Okay, that makes sense. And I guess the last question, commentary is, the thing in the security package for TPM support is really low-level primitives and a couple of commands like measurement. The OS guys use things like TSS or other things. So you guys, I'm guessing, had to curate your own bespoke, like a mini TSS for a lot of the capabilities you've talked about. Build your own libraries, I guess.
And I think that's actually one area we need to work on, right, in terms of EDK20, I know, right, in expanding TSS marshalling libraries over there. But yes, we do have a primitive functions at a lower level to deal with actually talking with the TPM, and we do use the current headers from the Tiano EDK2 base, right? But then you're still using functions like write and align or read and those.
Right, the NV access.
Yes.
So you had to create your own stuff on top of the primitive. Like
Yes,
you had to roll it
basically.
yourself.
So, and I think it would be great if we could just kind of port the OS marshalling functions to the firmware level.
To
That makes it
everyone.
easier
Okay,
for
it's more
everyone.
reuse. Makes sense. Thanks. Good talk.
We'll cut it off there for now, but thanks, guys. Thanks for listening.